Put simply, the rate at which something moves, which on paper isn't exactly all that exciting. So why have humans been fascinated by it since time immemorial? Why do we keep detailed records of the fastest and slowest of everything from snails to spacecraft to motorised sofas? The garden snail moves at 0.001 kilometres per hour, the Parker Solar Probe travelled at 586,800 kilometres per hour, and the fastest motorised sofa 161 kilometres per hour. So where does this obsession come from? Why do humans keep seeking to go faster and further more quickly? 13.8 billion years ago, the universe began with a big bang, and it's been expanding at speed ever since. And ever since we turned up about 2 million years ago, speed has enraptured us in all its forms. But what about it makes it so alluring? How does it connect everything together? Is it time to slow down? Well, that's what we plan to explore in this film. For as James Joyce wrote in The Dubliners, rapid motion through space elates one. This is our story of speed. Over the past 200 plus years, countless discussions, debates and lectures around the many facets of speed have taken place right here at the Royal Institution's iconic lecture theatre in central London. My name is Amy Reynolds and I've been covering the world of rapid motion for the past decade. And I'm pleased to be your chauffeur of speed for the next 100 minutes or so. Speed itself is nothing more than a measurement. It's not a physical thing like this desk or something that can even be twisted and warped like space and time. It just is. And it's not necessarily a concept we tend to spend a lot of time considering, unless we're on the motorway or keen for some early 90s action movie nostalgia. But the effects and limits of speed are all around us. The Cosmic Shambles network has somewhat of a reputation for cramming as much as humanly possible into one show, and this film is no different. It's not just going to be stories of human beings going fast. We're going to be looking at how speed connects us across all manner of areas, from the depths of space to the dirt in the undergrowth, from climate to healthcare, from race circuits to savannas, the sporting field to inside our own head. We're going to look at things that move very slowly and the things that move very fast, the things that are speeding up and the things that are slowing down, and ultimately why all of this matters. The idea of speed as a scientific measurement has been around since at least 330 BC, when Aristotle wrote of the speed of falling objects in his aptly named book, Physics. But it wasn't until the late 1500s when Galileo defined it in the terms we think of it today. Basically, a measurement in which we consider the distance covered and the time it takes to do so. To explain it slightly less basically, here's mathematician Matt Parker.
So my first experience of speed, like most people, is kind of lower secondary school. When that's like the very simple, straightforward, speed is just the distance you've traveled divided by how long it took, which is the classic speed triangle, if you will. But what you really care about is you want the instantaneous, like the speed right now, like how is it changing on a tiny, but then you're doing derivatives. So I'm afraid we're gonna have to write something down. Let's say we're gonna define everything as relative to this point here. This is distance 0. So you need some reference point everything's measured from. We're not gonna do relativistic speed. I imagine we'll cover that later, but for now, assume my whiteboard is not going a significant percentage of the speed of light. At some point, you're gonna have your first measurement. We're just gonna call that R1. That's the first measurement we're gonna take, and it's gonna happen at T1. That's at some time T1. So you're here, and then sometime later, you're over here. And that's now R2, and it's a different time. It's now T2. By taking the total distance you've traveled, which is how far away you were at the end of the journey, subtract how far away you were at the start of the journey, and then you divide that by how long it took. So same deal. It's the change in position divided by the change in time, and that is speed, sort of. Because this is assuming you go from the first point to the second point in the most boring way possible. It's just your average speed across that. We have no idea what's going on in the middle. And to capture that kind of nuance of the journey, well, that requires derivatives.
Before we let Matt get too far into the weeds with his derivatives, let's take a step back, a big step back, to where speed began.
So if we think about what happens in that sort of first few tiny fractions of a second of the universe's life, when space and time itself were created, humans couldn't have a speed before then without space and time, because in those first few fractions of a second, something happened that we call inflation, that took the universe from unimaginably small to larger than the observable universe is today. In the tiniest fraction of a second, it increased in size by 100 trillion times.
What we're pretty confident about as astrophysicists and cosmologists is that we observe the universe expansion accelerating, and we've invented this term called dark energy to explain it.
I remember as a student, so pre-1998, all textbooks said, the universe is expanding. It got set off in its expansion at the Big Bang, and now gravity is putting the brakes on the expansion, because that's what gravity does. It's trying to stop this. It's, you know, you're stretching a spring and gravity's trying to pull it back together again. What we didn't know was what is the ultimate fate of this expansion. If there was enough mass, then at some point the universe would reach a maximum expansion and then recollapse on itself. If there wasn't quite enough mass, maybe it would expand and finally come to a stop, or it could expand and finally reach just some steady speed and carry on forever at that speed. No, the universe is never going to reach a maximum expansion and recollapse. In fact, it's getting faster. They're looking at distant galaxies and saw they were expanding slower than their distance suggested they should, according to this formula that Edwin Hubble came up with. What does it mean for them to be expanding slower than they should be? Well, it means that since what we're looking at are galaxies in the distant past, because it's taken light so long to reach us, that expansion that we're looking at is something from very long ago. And it was slower then than we expect it to be. Therefore, it must be expanding faster now. What we now call dark energy is the thing that we use to explain why the universe is expanding ever more quickly.
Dark energy is a placeholder for we don't know.
We don't know what it is.
It's just pretty maths and clever ideas. That's what makes it fun.
The formation of the solar system, of the planets in the solar system, is completely tied into the formation of the sun. So I think 98% of the mass in the solar system is contained within the star in the center, within the sun. And then what you're left over with starts spinning out into a disk. And then that disk kind of swirling around your star in the center, clumps start to join together under the force of gravity again, and that's how you get your planets. It takes maybe, a few million years to get to something, I think, that looks like a planet.
There's a lot of physics in geology, and a lot of the Earth's surface processes or plate tectonic processes as well are driven by the same physics that dictate many other things in the natural world. It's about 200 million years ago, 170 million years ago, we had a supercontinent on Earth called Pangea in the geological past. This continent started to break up and form what we now know as the current position of the Earth's tectonic plates and the main land masses and ocean masses. To do that, Pangea moved between 2 and 9 centimeters per year and up to about 20 centimeters per year to move. And that's looking at the motion of the Earth's tectonic plates over a relatively long period of time. So what's 2 centimeters a year or 9 centimeters a year? Well, those sorts of rates are the speed at which your fingernails grow, okay? It's fast geologically speaking, it's fast in terms of the Earth's tectonic plates, but it's 20 centimeters per year. If I move 20 centimeters to my left now in 365 days, that's super slow. That's incredibly slow. So in a few tens of millions of years, because the Earth tectonic plates are continually moving sideways, up and down, the Earth will look completely different. It will be unrecognizable to us now. We can try and predict, though, based on where the tectonic plates are moving and how fast they're moving now, what it will look like, but we won't be around to see it.
But while we are still around, we keep on keeping track of various speeds, be it continental drift or the fastest water jet-powered car,
26.8 kilometers per hour.
And when you want to know literally any conceivable speed record, there's only one place to go.
Guinness World Records has been in the business of collecting speed records, amongst many other records, of course, since 1955, so that was the publication of the first book. The whole thing started, in fact, about a debate about speed. It was what is the fastest game bird. So Sir Hugh Beaver, who was the managing director of the Guinness brewery, and was invited on a shooting party, and all the men there who were shooting couldn't answer the question. They had an argument, and so Sir Hugh realised there'll be people in pubs up and down the country arguing over things, and they realised that what they needed was a book of records. So it's finding the fastest, the slowest, the tallest, the heaviest. Speed is, it's the ultimate definition of human achievement in one sense, because it's important for things historically, like cavemen running from saber-toothed tigers. Speed became very important. Or if you're running to resources that are running out, speed is important. So obviously speed is a fundamental part of our existence. I think people are excited by fast things, roller coasters and cars. And the fastest roller coaster in the world is the Formula Rossa at Ferrari World in Abu Dhabi, which can accelerate up to 240 kilometers an hour.
As long as we're talking about, and we'll continue to talk about, things like kilometres per hour, it's worth remembering that a unit, like a kilometre, is just something we made up. So is an hour or a second. They are irrelevant in the sense that the speed is the speed. We could choose any unit we wanted, how many times a hydrogen atom vibrates over a set period, the space between any two random fixed points, how long a duck is. It doesn't matter, but once we've accepted a universal definition, measuring that speed accurately and specifically requires a bit more maths. And so it's back to Matt and his derivatives.
We're going to try and capture everything that happens in the journey by plotting it. So this is time, and this up here is your distance. You're going to start here, T1, R1, and we know at the end of it, you're over here. You end up there at, let's say you rapidly accelerate to there. So in a very short amount of time, you're practically all the way there. But then you stop. Oh, I forgot that thing. So now we've got a much more complicated journey. But what you really want is take your instantaneous speed. So you pick a moment and you're like, okay, well, what was happening here? Well, at this point, if you zoom in on that part of the plot, you've got your line in here. And the moral of the story is, if you've got some crazy journey line, if you zoom in close enough, it becomes a boring straight line. And so now we're right back to our original situation. We can take what's effectively the average speed, but on a much, much smaller scale. And that's what your speedo in a car, your speedometer, is basically doing this at any point in time. What you can say, though, in more general terms, is you might want some kind of function, which just tells you how your position is changing. And R is a function of time. So you put time in, that tells you what your position is. That's where you are. The first derivative is what the slope is at any point in time. And this was the big breakthrough with Isaac Newton. And then you've got your first derivative, which looks very similar to before, where I had a triangle, small change in R divided by small change in T, but now this is like absolutely instantaneous. This is the first derivative of your position. That is your speed, and then your acceleration, that's the second derivative. And so now that's the rate of change of your speed, right? And you can keep taking further derivatives. So now, when we care about the exact details of your speed at every different point in time, what we're actually talking about is the first derivative of position. The issue is, as soon as you start getting down to these derivatives, it becomes real hard to perceive it. However, I believe, given this is a proper documentary, we have a way for me to experience that. To experience speed, the Shambles crew have organised for me to have a go on a MotoGP bike video game. And now I get to enjoy the giddy thrill of speed. And we've gone for bikes over like cars in F1, better acceleration. I got the accelerator on this side, which increases my velocity. And then I got the brakes on the other side that decrease my velocity. Slow, 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 slow. Oh. So as you can see, my speed is increasing, which means in the graph we were drawing before, the slope is going up. Or I've got just negative acceleration when I brake. That's just the slope brake, 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 and turn. By the way, in this game, you can set it to easier settings, which basically involves just toning down the laws of physics a little. But I was like, no, in a documentary about speed, we're going to keep the laws of physics on and accurate. So So there you are, that's the ins and outs of speed. My instantaneous speed is just my instantaneous tiny change in distance over tiny change in time, and my acceleration changes that slope is the easy way to look at it. But basically speed is quite dangerous, and this is a fun way to learn about it.
Speed and our ability to utilise it unquestionably changed the world. From the internal combustion engine to jet engines to the internet and even PlayStations. It's shrunk the world in more ways than we could have imagined. But as well as making some things easier, when we push its boundaries, there is no doubt that speed can be quite dangerous. And yet, for some people, that's not only their job, but it's the very thing that drives them. And as Matt mentioned, there's nowhere where acceleration and the physical feeling of speed is more evident than in the world of MotoGP. The highest echelon of motorcycle racing, where riders can reach speeds of up to 365 kilometres per hour, which is why we headed to the British round of the MotoGP World Championship at Silverstone to find out why these men and women risk life and limb in the pursuit of more speed.
The guys who all really sort of kill it are kind of scientists, you know what I mean? Because when you're racing a motorbike, you're playing with the laws of physics. You know, you're trying to push the laws of physics as far as they go, but you are completely, your life, your success is completely in the hands of the laws of physics, nothing else. You know, people think motorbike racers must be stupid, but to get to that sort of level, to win multiple championships, you have to be highly, highly intelligent. I haven't met a sort of properly successful motorbike racer who isn't very, very intelligent.
I think when I was about 3 or 4, I was pointing out at motorbikes on the road going, I want that, I want that. So I guess I always kind of just wanted to go fast. You know, obviously, you know, this is a dangerous sport, and, you know, you kind of have to accept that, you know, from a young age, and you know, accept that there will be injuries. So, you know, it's about, you know, understanding how everything works with this thing, you know, different tires, different brakes, you know, there's a million things to understand, aerodynamics as well, so.
It's difficult to explain the feeling, because for me it's like something natural, because I'm doing this all my life, so for me ride a bike is like walk, it's something normal. Best thing of ride a bike is when you are racing, you don't have like the opinion of the people, so it's like you with your motorbike doing what you want in this moment. For sure the speed make it even better, but when you do it every day, it's like you don't feel this speed.
And the first time you'll do it, your brain will always be going, ah, 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 because it's new and scary and terrifying. It happens to everyone, so it will be happening to these people too. They will be just getting used to the situation, the experience of going really fast. And the brain learns quickly that, okay, I need to be able to handle this.
Well, the first time I really feel the speed, and I was scared because I was very, very young. I had 13 years old. It was the first time I was able to try the 125 GP, and I was too young to do that.
So when you're a teenager, you are more sensation-seeking in your behaviour, in your drives, your motivations, and your brain isn't as able to recognise the risks of doing so, or the negative outcomes. But then as you get older and quote wiser, because we know a lot of adults aren't in any way, shape or form, those parts of your brain, they become, they become more in sync with the emotional, impulsive parts.
To me, this is the thing that makes it different from everything else. Every time they get on the bike and they're doing 200 miles an hour down the straight, that could be the end, you know what I mean? So that they have to get themselves in that mental state where they are prepared to take that risk and perform under those conditions.
You know, humans compete. That's what they do. I always say about, you know, when did we have the first motorcycle race? Probably about a day after they built the second motorcycle. Risk is a part of life. There's obviously been a change in the way that we approach risk and accept risk. Racing adapts to society. So you see people looking for innovative ways to reduce risk. I mean, the most obvious is the airbag, for example. I mean, there used to be, people would just ride in thin leathers. But now, I mean, like I have my airbag, so it's already made my riding safer. It's making my life safer. A lot of racing is about developing changes, developing technologies which can be moved down into the consumer to actually provide a wider benefit. In a way, it's a little bit like the space. You know, why did we go into space? Why did we send stuff into space? Because you want to go and learn things. You want to find out things.
David's right, of course. Humans are by nature curious adventurers. We want to go to new places, discover new things, and usually we want to do it fast and do it first, be it on 2 wheels, 4 wheels, foot, spacecraft, whatever. Historically, we're not good at waiting. Well, Brits are, but that's another story. And there's good biological reasons for that, about why we like going fast, not why Brits like to queue.
And usually for this sort of thing, you go back to the evolution of our species. There would have been a tangible advantage to being able to go fast. Species with an enthusiasm for going fast would have had a greater chance of survival. And over time, those sort of things enter into your underlying neurology, the fundamental workings of your brain. But in terms of the basic raw processes, something called excitation transfer theory. So when you're going really fast, it's stimulating. It's very stimulating because you're doing something demanding, thrilling, and your body becomes excited, and you experience a visceral pleasure from that. All your senses are heightened.
I think one of the big moments is when I first tried the MotoGP bike. That was for sure. Once you get on something that's got 300 horsepower, it was pretty insane. So for sure, the first time you try it, man, the first time you open the gas, it's just blows your socks off. Eyes are wide open. You get full tunnel vision, and it's like, holy crap, this thing is fast. It's hard to hang on to the handlebars, honestly.
My dad was a rally instructor at a gravel rally school in the UK, so I went to work with him and sat in the passenger seat, and I was so tiny I couldn't even see over the windscreen. But I remember just seeing the tree line. We were in a forest, and I remember seeing how fast I was going through this forest in this rally car. And I remember it was my dad, so of course you trust him with your life, you never think he's gonna crash. And I remember the adrenaline feeling. It was kind of like a fear, but with adrenaline, the kind of thing you have at a theme park.
For most of us, the easiest way to feel the enjoyment of speed might be to ride a roller coaster. Theme parks, coincidentally, are the one place where you get to combine the fun of queuing and going fast. We're so excited by the prospect of 30 seconds of speed, we'll queue up for 2 hours for it. At a theme park, as long as you're taller than this, you can ride as many times as you like. But in the MotoGP paddock, be it through injuries or age, there comes a time when riders have to hang up their leathers. So when you've been racing almost as long as you can walk, can unnatural speed and the adrenaline it provides become addictive?
The simple answer is yes. I mean, we can become addicted to anything, but we don't. We use addiction sort of colloquially all the time to mean all sorts of things, from like, oh, I'm addicted to this new ice cream or this computer game or what have you. And most of the time people just like these things.
It's difficult to stop this because you can't feel it in another activity on your life. It's like many riders stop racing motorbike but then start racing car or...
Probably do something with cars.
It takes a while to wear away, I think. I don't think they have an easy life for the first several years, really.
So when I stopped, the kind of whole acid house thing was exploding. So that was my kind of way of getting my thrills.
Like anything, the more you practice riding a motorcycle at absurd speeds, the better you get at it. But the thing with extreme speeds like those in motorsports, the more you do it, the more your brain actually starts to change how it perceives the speed, as if time itself is distorted.
When you think you know how long has lapsed between two events, so like when you're riding around a circuit if you're a motorcycle driver, or simply when how long you've been sat at your desk or something like that, then you're using your internal clock as a reference, and that is a bit magic. I mean, we know how it works on a cellular level.
You kind of have like an internal clock, let's say, where you know whether you're on a good one or a bad one. I wouldn't say we know that it's, a 10th faster or a 10th slower, but we can kind of guesstimate, I think, and I think we're all pretty good at it. We've been doing it, all our lives, and I think all of us can do it.
The rider can feel a tense. I can feel easily which lap time I'm doing when I'm doing the lap time. So you don't feel the speed, but when you brake, you realize how fast you are.
But the perception of time passing rather than knowing what time it is. That's very different. People who've been in car accidents always say, yeah, time suddenly slowed down, you know, because you suddenly find the car swerving or flipping, and it's like you're moving in slow motion.
On the bike, you feel everything slow, and when you lose the control of the bike, normally it's quick, but the crash you feel is so long. Depends which crash you are doing, but and you just pray to don't get hurt, and you feel the crash is very long, too long.
So at that moment, either your perception or your recollection of it, I guess you can probably train yourself to be able to detect time, detect speed. In most people, it's an absolute thing that you always perceive the speed at which events are happening at a constant rate. So the speed may be changing, but our impression of that speed is also changing.
Of course, racing isn't the only thing that alters your perception of speed and time, and that is why vehicles and mind-altering substances should never mix.
Psychoactive substances really impact on our perception of the world around us, and also our kind of internal perception of our own body's space in the world as well, so what we call proprioception. So you can imagine that if you were in a fast car or in an aeroplane or something like that, that if you were having things that were changing how you saw and heard the world, that would really impact on your kind of sensation of experiencing speed and movement. So amphetamine is called speed, which is a stimulant, might improve your reaction time. However, it's not going to improve your accuracy, and in fact probably quite the opposite. So you might be much quicker at responding, but you might not respond in a useful way. So I think we can see this when we do scientific experiments where we do what's called a go, no-go task, where things flash up on the screen, and if it's green you have to click one button, and if it's red you have to not click that button. People are really fast at clicking on green, but they just keep clicking on red as well, because they're like, yeah, thing, and they can't withhold their response. So that's the kind of impact that stimulants have, is that they might increase your reaction time, but they also remove that inhibition that is quite important in lots of circumstances. Yeah, so alcohol and other depressant drugs increase your reaction time, so you're slower to respond to things that you see, and so that can obviously then impact on your ability to perform tasks like driving, for example, because moving at high speed, when your reaction times are slowed, your concentration is impaired, and yeah, you might be feeling quite sleepy. Terrible idea.
So how fast are our brains sending us signals? How quickly are we forming experiences? What is the speed of thought? The best way to investigate this might be to start off with one of the fastest, most tangential connection-making brains there is. Who else but comedian, and as The Observer once noted, the Bacardigan polymath, it's Robin Ince.
The thing that I love about the speed of thought on stage is that it manages to be so persistent that the negative thoughts don't come out, which is one of the great things, which is, I think, part of the reason that I love stand-up.
And I've realised that this, you probably are just sitting there going, I have no idea what's going on. But the good thing is, neither do I.
There's thought after thought after, and I do know that even in any, well, usual situation, but in fact, in particular in a live situation, whether it's stand-up or whether it's interviewing someone,
I'm not sure it's a speed thing, but I think what it is that Robin is interested in so many different things, whereas your average person has like 2 or 3 interests, and they can explore those in depth, at length. But Robin seems he's interested in literally everything. Again, there are pros and cons to that. Obviously, it makes someone far more creative. But when you ask him a question, you could get anything as a result.
Something that Brian Cox has always had a go at me for, in a jocular physicist manner, is when I ask questions to scientists, or anyone really, very often I start asking one question, it becomes another question halfway through, and then by the end of it is a third question. And so quite often there will be a moment where an epidemiologist or a geneticist will say, sorry, what was the question? And then I have to try and work out what the question was. So that even just in that situation, there's a speed of thinking, which is, I want to ask that, no, I want to ask that, no, I want to ask that.
You could argue that the maximum speed of an impulse through a sequence of neurons is something in the region of a third to half the speed of sound. So that's probably the speed of a thought in terms of it's going to go from 1 to 2 to 3. In that respect, I mean, that's the physiological speed of thought, I suppose. If you consider a thought being a combination of signals travelling through neurons, which it is, so that would make sense.
I think since the since the kind of the news of the high possibility of ADHD, one of the things that has changed is I used to worry night after night that before I'd gone on stage, I would sometimes have in my head, like on the train there, I could see myself standing up and saying, hello, welcome to my eloquent but lightly amusing discussion about the nature of the art of Louise Bourgeois. And then, of course, what actually would happen is the moment I hit the stage, I go, oh, right, there's something I need to tell you about spiders and something that I need to tell you actually about urban myths and something I need to tell you about. And then I would come off stage and think, oh, I meant to deliver them this really clever show and I didn't do it. And then I realised that actually what the audience had liked for a good decade or so was the fact that they saw a different show every single time and what are the stories that he's not going to finish telling.
I was going to tell you about my first gig, but I don't... What time... Whoa! This is how many we've done. This is how many we have.
Or maybe like you pour water on a really hot surface, because bubbles just like flying around. That seems to be, that's more what Robin's brain is like, I think. It's just like, right, drop this, let's see where that goes. Well, that was unexpected.
I think it was University College London. They were doing some research into what happens when you're improvising. So basically, a bunch of comedians and public speakers went into an fMRI, obviously on different days, they're not roomy. And in the fMRI, then you would be given various different words and you would just have to talk for 30 seconds about them. What they found with their control group is if you ask someone who is just entirely normal and doesn't show off for a living to talk about bananas for a minute, they can't, because that's not how they're used to. Why do I talk about that for a minute? Whereas, of course, you know, comedians and public speakers are used to just going, oh, I better make up some rubbish here. But what they generally found was that the speed of thought you might see in a performer, there's nothing you can specifically see in the brain except for the fact that it seems that the motor area is so used to jabbering on that your brain doesn't need to worry about it as much. So in terms of blood flow, etc., to the parts that involving the motor area, it doesn't blah 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 blah. We're used to going blah 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 blah. So the brain goes, oh, it's fine.
Unlike some other networks that we won't mention for legal reasons, we're not interested in balance for the sake of balance, but to be fair, not everyone is interested in speed for the sake of speed either. Physicist Dr. Helen Chersky expects your thrills to have a point.
Speed by itself is just a dangerous thing. But if you can do something interesting as a consequence of that, then I'm all on board with it. And going fast by itself, you know, it's just a way to get somewhere. If you can do something interesting on the way, if you can see something, like going fast enough to escape Earth's gravity and go into low Earth orbit, that's speed that takes you somewhere interesting, right? But what's interesting is getting into low Earth orbit. It's not necessarily the whoosh on the way. And I guess I've just always been more interested in the ideas. The act itself, the thing that looks dangerous, is actually, it's a piece of precision engineering. But it's the precision engineering that's gone into it, which is the interesting bits.
When it comes to something like the land speed record, it might seem to be exactly the sort of thing Helen is talking about. Going fast for the sake of going fast.
The official land speed record, set over 1 mile, is 1,227.985 kilometres an hour.
But that's not necessarily the case, because it's also true that every time we go faster, we learn something new. That's certainly one of the driving forces for the team at Bloodhound LSR.
Bloodhound is a fantastic way to inspire that next generation because kids innately love speed. I'm passionate about it, and I know we're one of the biggest STEM inspiration projects in the UK, and if we were to go and break the land speed record, that could add huge benefit to the country in terms of more people choosing to choose science and engineering when they're older. Fundamental thing about a land speed record is its history. In 1904, they only just went above 100 miles per hour. It's a short time frame, and with engineering and science that's rapidly accelerated then, the speeds have increased massively. And ultimately, there's this innate part of being a human being. We want to push boundaries, we want to push limits, and the fundamental one is speed. Bloodhound went out to South Africa in 2019, and the tests were extremely successful, and we achieved a top speed of 628 miles per hour. On paper, through the modeling we've done on supercomputers, this car ultimately could do 1,000 miles per hour.
Aerodynamically, I guess one of the key things that happens when you push vehicles to the speed that we're trying to take Bloodhound is that you pass through the sound barrier, or Mach 1. And that's where interesting stuff starts happening aerodynamically. But it's not an absolute limit. We know we can go there. We've taken a car there before, and aircraft commonly go through this thing called the sound barrier, or Mach 1. So when you approach the speed of sound and go beyond the speed of sound, we generate these phenomena called shock waves, which are effectively instantaneous changes in the properties of the air, the pressure, the temperature, and so on. And they cause all sorts of aerodynamic headaches. So you get a big buildup of drag as you approach and exceed the sound barrier. But also you can have adverse effects in terms of the lift or downforce that's being generated.
It's extremely challenging now. We are really pushing the limits of, engineering. The empty space up here is for the EJ200 jet engine, which is loaned to us from the Ministry of Defence. At the bottom, that's where the rocket goes.
So we made the decision very early on that the entire aerodynamic design process for Bloodhound would be done by computer in the virtual world. So at the end of the computational fluid dynamics process, we end up with this sort of thing, okay? So we've done the maths, we've done the number crunching. So what we're seeing here are one of the things that we look at straight away, which is the pressure distribution over the vehicle. And on the left-hand side here in particular, we're interested in, well, what are the pressures doing on the underside of the vehicle? We know if we get too much high pressure underneath of the vehicle, that generates lift. So on the right-hand side, we're looking at the actual surface, the desert surface, effectively, that the car is rolling across. Because one of the things we were very concerned about, certainly in the early days of the design of Bloodhound, is how much damage would we do to the surface? Would the shock waves generated by the nose of the car completely destroy the surface so that the rear wheels didn't have a surface to roll across? This isn't an application we're going to see everybody driving around in 20 years' time. But we've developed modelling technology specifically for Bloodhound that we can now filter out into other more conventional applications to help make more conventional vehicles, aerospace vehicles, more efficient in the future.
There are many other car records.
The world's fastest lawnmower was clocked at 230.446 kilometres an hour.
The ultimate one is the outright land speed record because it's simple. There are very few rules. You drive a Formula One car, oh my word, to get out the book of rules, it's so complicated.
Yeah, so we cannot design everything we want. We have regulations, so it's a bit difficult to work around those rules. For example, when you design a part, if you design a part that creates more downforce, it also generates more drag. So you need to find that balance, what you want. The car behind me from 2012 and this year's car might look the same, but there's actually quite some differences. It's less advanced because the FIA, the FIA, wants the teams to be closer to each other in terms of speed, so it's more interesting to watch the race. Certain teams were quite big, had a lot of money, so could develop the car more because they could hire more people, for example, and other teams were smaller, didn't have as much money as other teams. But this year there's a financial budget cap, which is equal for everyone, so everyone has the same budget to develop the car.
The Formula One cars have nailed it. They've gone through all sorts of optimization cycles to get the underside of the car tuned. An increase in velocity results in a drop in pressure, and it's effectively sucking itself down onto the track.
What I do is I design components on the floor. When a car goes on a track that has a lot of straights, you obviously want to minimize drag. But when you have a track where there's a lot of corners, you want maximum downforce, because in corners you need downforce for the car to stay attached to the road, to go fast through the corners. Then from that understanding, I refine the design of the part I designed. And then we send it to the wind tunnel and we test in the wind tunnel.
So the way a wind tunnel works is pretty straightforward, really. I mean, essentially it's a glorified hairdryer. I mean, we're just blowing air over a physical object that we will manufacture.
And from there, if that part was successful, then we send it to the track to test it there before we race it. So if it was successful also on track, we race that part that weekend. So we don't get bored in Formula One, that's for sure.
In the case of a company like McLaren, they're not just a leading Formula One team, but the manufacturers of some of the most elite supercars for the road. And for the IET Young Woman Engineer of the Year for 2020, Ella Podmore, speed is about a lot more than the aerodynamics and engine power.
At McLaren, we tend to think of speed as power to weight ratio, and the better our power to weight ratio is, the faster the car effectively goes. So of course, what can we do to reduce that amount of weight? Making smart material choices, what we're making our components out of, something that has less mass, something that's stronger so we can use less of it, is all going to make our cars more lightweight. So carbon fiber is a composite material that is very close to McLaren heart. This material, I think, has been revolutionary for what we consider being the lightest, strongest material that we can work with, but also very bespoke. The way that we can manufacture it, the way that we can design things with it, allows us to do all sorts of crazy stuff. And that's beneficial to us all, saving that weight, but making it stronger in places that we need it, but very thin in other places where we don't need the mass. Materials are getting stronger. We're mixing elements into the likes of those old metallic alloys that we use to make it lighter, to make it stronger. And that's a lot of work. What I do is making sure that we have the right contents of the elements in that aluminium to make sure that we do have a perfect compromise of it being lightweight, but then energy absorbing as well. Then also it's safe.
Once again, the faster we go, the more we learn. Now, let's say you somehow got the chance to drive an F1 car around a racetrack. You'd probably feel like you were traveling at a lot more than the near 400 kilometers per hour one of those cars can reach. And yet, you've quite likely traveled at almost double that speed without feeling like you're moving at all. A large passenger jet travelling between, say, London and New York is cruising through the air at around 900 kilometers per hour, and yet your experience is one of just sitting still. In fact, if there's a crying baby and a terrible movie selection, it could even feel like time has stopped. Your personal experience of speed plays a huge role in your understanding of it. And of course, if we zoom out, right out, at this very moment, we're all moving at around 30 kilometers per second as the Earth hurtles through space. Once again, it's all a matter of perception.
All motion is relative, and this is something that goes back long before Einstein. Newton and Galileo have a theory of relativity.
If we start with just, for example, the Earth rotating, the Earth rotates on its axis once every 24 hours or so-ish. But you've not just got the Earth spinning on its axis, the Earth also orbits the Sun as well, which it does at 30 kilometers a second. But then you've also got the Sun itself orbiting the center of the Milky Way, which it does that at 230 kilometers a second. But then you've also got the Milky Way moving through space as well, which is a little bit harder to measure because you have to measure it relative to something. So the thing we use is the cosmic microwave background, that glow, that relic of light from the very sort of early days of expansion of the universe. And the Milky Way is moving through space at 583 kilometers a second.
And yet, we're not aware of that motion. What we talk about is that the laws of physics are the same regardless of your state of motion. You can't find a frame of reference which you can say, that is definitely not moving. The nicest example is that if you're on a plane and you're sitting at the back of the plane, the air steward or stewardess that's pouring the coffee doesn't have to start pouring the coffee at the front of the plane because the plane is going to move towards it and you'll catch it in your cup when you arrive. They pour it above your cup in exactly the same way as they were doing on Earth if you were not in a plane. And the same goes for why we don't perceive or sense the Earth's motion through the universe.
Oh, and as long as we're talking about time, we should probably point out that all this goes out the window if you find yourself in the unlikely but highly unfortunate situation to be passing by a black hole.
So we can think of mass doing something to time and doing something to space separately. And what we perceive is that time gets slowed down by gravity. And of course, if gravity is very strong, like in a black hole or near the event horizon of a black hole, then time slows down a lot. That's probably another interview.
We literally don't have time to get into time. Constant speed without a frame of reference feels like no motion at all. Think of being on a train, looking out the window and seeing another train travelling at the same speed. It doesn't look like it's moving at all. Or if there are leaves on the tracks, maybe it isn't actually moving. The point is, it's the acceleration that gets you. Even more so when that acceleration is courtesy of a near 300,000 kilogram rocket sat right beneath you. No one in this documentary has experienced rapid motion through literal space quite like Helen Sharman, who became the first British person in space as part of Project Juno in 1991.
When we launch, we're aiming ultimately to get to a similar speed to the space station, which we want to reach. And that's traveling at about 28,000 kilometers per hour. That's just over 17,000 miles an hour, about 8 kilometers every second. So the launch itself ultimately has to take us there, except the launch really only gets us halfway. So we launch to an orbit of about 200 kilometers above the Earth's surface. The space station is about 400 kilometers high. And then we need to do a series of maneuvers to actually increase the height of that orbit. That orbit needs to be higher. And in getting higher, we need to make ourselves go faster to reach that height. But because we're not going along flat, also along in a straight line over a flat surface, it feels a bit sort of counterintuitive that although we go faster, as we get further out into a higher orbit, we actually slow down. Because the odd thing is that the lower your orbit, the faster you're traveling. And it makes sense when you think about an orbit is really, it's not just about speed, but it's about energy. And you know that the further up you lift something, the more potential energy it has. And then when you let it fall, it loses potential energy and it gains kinetic energy. So a lower orbit has less potential energy, but more kinetic energy. So we're in a lower orbit to the space station, so we're traveling faster. It means we're going, we start off just sort of behind the space station and we catch it up. And then we need to boost the orbit. So we need to actually go faster to go higher, but in so doing, in going higher, we actually then go slower again. So it's a kind of a counterintuitive sort of maneuver. We have to go faster in order to go higher and slower to catch up with the space station. Once we've stopped accelerating, we feel stationary. It doesn't feel as though we're moving at all. The only time I knew we were moving was a spin, because the spacecraft has to actually, Soyuz spacecraft spins to keep its solar panels pointing at the sun. So if I looked out at one particular point for a few seconds and then looked back in again, the whole spacecraft kind of spun around me a little bit. It was kind of a bit weird. But it was only by going over the surface of the Earth I knew that we were going fast. London, pretty much the whole of London's gone in a few seconds. Western Europe, 5 minutes or so. That makes you realise how fast we're travelling. But I just felt as though it was completely stationary. The launch itself, I felt acceleration, not speed per se. I could feel being pushed back down into the seat as the acceleration built up. So I was, if you like, almost lying back with my chest up, back down, and knees pointing up. So I was just being pushed down into the seat as we accelerated away from the Earth's surface. And the G's built up. And then when the rocket stage is jettisoned, the G's drop again. And then they build up again with the next stage, and then they drop. And then they build up again with the final stage, and then they drop to zero. So it's that increase and decrease of acceleration that I felt, not the speed itself.
A lot of the facets of speed we've looked at up to this point involve human beings' fascination with finding new ways to go faster with science, engineering and mathematics. But for some of us, we're just trying to go faster and faster and react quicker and quicker, where the only limits are our own biology.
What pushes me is that whole idea of, well, how fast can I actually go? And it's that thing of not actually setting a limit to myself and just honestly thinking, you know what, if I actually work just that little bit harder, eat just that little bit better, I could be even better. And I just want to see what that better version of myself looks like. It feels like you've got a jetpack attached to you, and sometimes it can feel like you can't even believe how fast you're going. It's just like, you know what? I'm just going to go with the flow. The jetpack has taken off. My only job now is just to keep moving my arms, etc. It just feels fast.
In track and field athletics, the sprint starts are started with a reaction time limit. And originally it was set at about 120 milliseconds, so 0.12 of a second. But there was a lot of anecdotal evidence that sprinters were getting false starts and vehemently claiming that they weren't false starting.
One false start as a result of too much of a fast reaction results in you actually, you don't get a second chance, you're disqualified, you're out of the race.
When there's a loud sound, you get an involuntary reflex action that is predominantly initially being looked at for the face, but it actually is found to affect all the muscles in the body. And eventually they showed around 99 that not only could you get this startle reflex, it could trigger a voluntary movement of the feet. And this meant a typical person, an average person, could respond in well under 100 milliseconds, and they were getting electrical activity of the muscle in 60 milliseconds.
It's kind of hard to reduce your reaction in a way, because the position that you're in, especially in the starting blocks, you're not designed to stay in that position for a very, very long time. At some point, you have to be able to react. You have to be able to, hit your foot off of those blocks and go. But I guess that's where training is important, or at least the training environment is important, just to practice over and over and over again.
What's happening between the sound or the vision coming in, or the proprioception from touch, and it getting to the muscles to start their action. The speeds are the same across most animals, certainly across mammals. I mean, the time from start to finish might be different because an elephant's big and something else is small. But the nervous system conduction times, the times for the synapses to transfer information, those are all pretty hard thresholds. So that startle reflex is quicker because you go through a different part of the brain. Similar thing, touching the burnt hob and pulling your hand away and then saying ouch afterwards. You're not thinking, I've knocked my favourite cough off that's half full of coffee and it's going to fall off the table and hit my tiled floor. All that you've just got falling. There's the simplest cognitive thing that you are responding to. You can therefore think and adapt and improvise and respond in different ways.
How fast you are on the reaction and how focused you are make you feel slow, everything. You have to make a quick decision. I was feeling what happened and make the right decision. So in that moment you are so focused and everything going a bit slower.
People involved with optometrists who will train hand-eye coordination. And you can use these things, it's like a big board with little lights, so they come on at random places. And the training is basically spot the light, hit it with your finger, spot the light, hit it with your finger. And the first time you do it, you're missing by 1 millimetre or 5 millimetres, or it might be. The more often you do it, the more precise you are. And that's a very good way of training the eyes and the hands to react together. And basically you're doing, even if you don't have that sort of opportunity, you're doing the same thing each and every time that you stand at silly point. You're adding to your knowledge, adding to your instinct, so that when you see the ball go to your right, you're not actually going, thank you. It is that, and it's in there, or it's not.
Movement crab takes 300 or 400 milliseconds, so it does feel like you're thinking it through time, finishes after you've caught it.
And hopefully, most of the time it goes in because you've trained to do it.
Then what gets done and why people look like they got better reaction times or they look like they just are ahead of the game is because what they're doing is they're picking up what are called cues. They're picking up early movements that must precede what's then going to happen. There was an old BBC, sort of maybe in the 70s, showing a cricket bowling machine proving that cricketers can't react in time when the ball first came out of a cricket bowling machine.
I mean, the mathematics works out something like this. If someone lets the ball go at 90 plus miles an hour, by the time they've let it go from a yard or so in front of the stumps at their end and you're standing a yard or so in front of the stumps at your end, you're down to 20 yards, and that's about 0.4 of a second. Now, if you are thinking about it, you'll be too late. So everything you do in terms of training your brain and your body as you progress up the levels and up the speeds is about making sure that your instinct can deal with it without a real rational thought process. Now, if your instinct is good and you're watching things, I mean, for instance, if you look at the bowler's hand, whether it's Marshall, Holding, Garner, Croft, all the rest of them, if you're watching the point of release from the hand properly, that's your first clue. And that gives you the first clues as to the length, whether it's coming full at you, halfway down, or it's going to be passing your head. And therefore your instincts, once you pick that up, are already saying either I'm going to start to move my body forward, or I'm going to start to go back, or I'm going to start to duck. And if at any stage you think, I've got to rethink this, you've already run out of time.
The fastest recorded delivery in international cricket is 161.3 kilometres an hour by Shoaib Akhtar of Pakistan.
And for instance, when the ball is flying past your head, there's an exhilaration of seeing things moving quickly. When it's coming here and you don't get out of the way, there's a brief moment of exhilaration and a lot of pain. And when you're playing the shots that get you runs off those quick bowlers, that has everything going for it. I mean, there's the exhilaration, there's the satisfaction, there's everything. That competitive spirit, the competitive juices are flowing.
In every athlete, there's that competitiveness. So I guess even as I am walking the dog and I see someone, to the left of me walking, I'm thinking, okay, well, how quickly can I walk to this next lamppost or tree before the other person?
Running or going fast for fun is not exclusive to us humans, of course. Dolphins leap and play in the ocean, and anyone with a dog will recognise the enjoyment they get from chasing a ball. But when we think of speed with animals, or most things to be fair, we instinctively think of things going fast. We think of a McLaren, not a Datsun. But as I said at the start, speed is simply a measurement, so that means we've really got to look at things going slow as well. Faster isn't always the aim, and it isn't always needed, and that doesn't make it any less interesting, because in nature, speed truly just is. To really get a grip on both ends of the speed scale, we headed to the north of England, to one of the world's leading conservation-based zoos, Chester Zoo, to meet Matra the cheetah and Rico the sloth.
So sloth have always been labelled this slow creature, but actually if you delve deeper into them and take an interest in them, actually they're perfectly adapted for their environment.
I'm not sure there is really any difference in the rate of evolution between multicellular organisms and simpler or smaller organisms. Evolution is simply a process that takes place, this change ultimately in these frequencies of different kinds of genes. Natural selection is one of the main ways that can change, but it's not the only way. Selection isn't trying to make species. Species are accidents.
Their eyesight is very, very poor. So if you can imagine a primate, for instance, that can move very, very quickly in and around the trees, a sloth doing that would come up, would probably fall many times and they would stay in the trees. So they evolved actually to move really slow, very precisely, which will avoid them falling, which sloths do on occasions. They can move along the ground, but it's very, very slow.
The slowest mammal is the three-toed sloth of South America, Bradypus tractylus, which has a ground speed of up to 2.4 metres per minute.
However, in water, they are very good swimmers and actually quite quick. Their food is predominantly leaf material, very low quality diet. In fact, it can take up to about 30 days for them to digest a leaf. So very, very slowly moving through the body.
Yeah, so the cheetah is the fastest land mammal.
The fastest mammal on land over short distances is the cheetah, which has been timed at 110.07 kilometres an hour.
So it does about 0 to 100 metres in about 5.9 seconds, so it's about half the time of Usain Bolt. So yeah, very, very, very quick. So if you look at a cheetah, they've evolved so well for what they do. So they're really slender, really streamlined. So when they start off on the hunt, they have protracted claws, unlike other big cats. So their claws act like football boots, grab some traction on, and that's how they can get accelerated. Then once they're into their hunt, they go really streamlined, almost into a bullet shaped in the air. So they actually spend most of their time in the air when they're hunting. And then they've also got these massive nostrils, so that helps to intake air, so they can get really enriched oxygen blood through the heart and their lungs. So some of your bigger cats, they sometimes eat only once a week, whereas a cheetah will probably have to eat once a day, once or every other day, to get the energy that they need. They can last a little bit longer than a full Thompson's gazelle, but yeah, they have to eat a lot more than a larger tiger or a lion would.
There are various forms of antelope in Africa which can run very, very fast away from a predator. but they don't. Instead, they pronk. And the idea is that what they're basically saying to the lion who they've spotted, don't mess with me, mate, don't bother coming with me. I am so strong that I can see you, and I'm just doing this to show you that I'm really, really strong, because if I have to, I can actually run like the wind. So sometimes you don't actually need to be able to run fast to avoid predators. You just need to be able to convince the predator that you could.
One of the key aspects of speed in nature that the research teams and scientists at Chester are concerned about is the speed of habitat destruction and species extinction. They've been working hand in hand with colleagues around the globe to slow down this sudden and dramatic crisis of the natural world. And 2 programs in which they are world leaders involve some very tiny, very slow snails and some annoyingly fast toads.
So the first thing to understand about toads in Madagascar is that there shouldn't be any toads in Madagascar. Madagascar has got a huge amphibian diversity. We've got about 300 species of frog, over 98% of which are endemic, but there shouldn't be any. There are no native toads to Madagascar. So when toads arrived, the whole Malagasy ecosystem was completely naive to toads and doesn't know how to deal with them. The issue with these toads is that they're toxic, so they exude a compound from the parotid glands, which are on their shoulders, and this compound is toxic when it's ingested by predators. So the problem that we're having is that Madagascar has got a lot of predators that are evolved to feed on frogs. They're now feeding on these toads because they don't know that they're toxic, and we're seeing mortality events in native predators in Madagascar. Other prey species in Madagascar they're experiencing what we call predator release. So those prey species are increasing. One of the main ones are actually rats. And Madagascar is a country where a huge proportion of the population is suffering from food insecurity, and there are also plague outbreaks almost annually. So if we see an increase in the rat population, then actually the impact on the human population is going to be devastating over the next few years. Their reproductive speed is astonishing. So a single adult female sexually mature toad can produce 8,000 to 10,000 eggs every year. Let's say we had 500 adult female toads and we eradicated 98% of them. Just that 2% remaining would still be producing tens of thousands of eggs every year. So even after just 1 year of our relatively effective eradication program, the population will have rocketed back up again. So we're trying to target our efforts to areas of high biodiversity value where we can try to mitigate the impacts of these toads.
So in this room we've got 2 different species of Bermuda snails. We've got the greater Bermuda snail and the lesser Bermuda snail, and they're both endemic to the islands of Bermuda. So this is a custom built room for them. It's approximately 2 by 6 metres and we've got just over 30,000 individual snails in here at the moment. So we started with our first snails here in 2016. These ones were the last ones that were found alive left in the wild. We thought they were extinct before that. So we started with 60 snails and we set up a captive breeding program here for them. And in that time, they've multiplied lots and lots, and we've been able to release about 90,000 animals back to the wild in the last 3.5 years. With this species in particular, we've definitely gone above and beyond for as quick as we could act. I don't think we could have got in there much quicker and released as many animals in the time that we have. So yeah, not every species is going to be as easy to save as this one, but it is important that we try, and especially when you're starting at the bottom of the food chain like these snails are, that's one step that you can take to make life a little bit easier, because smaller animals tend to breed a lot quicker and they'll support the food chain from the bottom upwards as well. The populations are growing by about a radius of about 10 metres per year. So that means they're travelling. It doesn't sound like very much, but when you're a 2 centimetre snail, it's quite a lot. They're thought to go around 0.001 miles an hour. Yeah, and we've definitely seen signs of breeding and new generations out in the wild already, so it's going really well.
All too often when we think of nature, we think almost exclusively of plants and animals. But of course, the natural world concerns so much more.
So where we're standing here at the moment in the north of England is probably moving a couple of centimetres per year. So where we're standing at the moment is also going up by a few millimetres per year as well. And I would argue as a geologist that whether things go up and down, it's as important to me as whether things go sideways as well, and the speed that both of those processes occur at. The speed in which the Earth goes up kind of controls how fast the landscape is eroded into and cut into by things like rivers. So the faster it goes up, the more likely it is to be eroded downwards as well. So there is a relationship between the speed at which the Earth goes up and down and the landscapes we find as well. It's the subduction, so when one plate gets sucked down beneath another plate and the heating up of that plate, that drives the generation of magma and therefore drives the formation of volcanoes as well. So the speed at which the Earth's tectonic plates are moving effectively regulates those other geological processes.
The ocean is always moving. It's a liquid, it's relatively easy for liquids to move, but the surface of the ocean is interesting because it's full of patterns. It's full of patterns of movement. And by our standards, those speeds can be relatively slow. So for example, the Gulf Stream might move on a good day at 2.5 meters a second. That's about 5 miles an hour. It's not super fast. But when you think about the amount of water that's moving, it's a lot of movement. So the big features of the ocean are these gyres, where you get these kind of big roundabouts that fill an entire ocean basin. And on one side, the flows are very slow, but on the other side, you get this process called western intensification, and it speeds everything up, and that's what the Gulf Stream is. It's just one side of this roundabout, so it goes very fast around the Gulf Stream, and then it goes slowly around the other side, and it comes back, goes very fast around the Gulf Stream again. And so those are the places where you get the highest current speeds in the open ocean. And the other place you get really high speeds is where there are huge tidal flows. So for example, in the places where you get a high tidal range, but there's some kind of narrow channel, but there's space for the water to go on the other side, water can just rush through at very high speeds. I think the fastest flow speeds in the world are likely to be about 10 meters a second, 20 miles an hour-ish. There's lots of species that use things like the Gulf Stream and these big gyres to hop onto them, get carried by them and then hop off at the other end. So turtles use gyres, for example, as they just get carried along with them. And if you've got a good food supply and your food supply is being carried along with the current and you get carried along with it, that's great. And so currents are really important for biology, not just because they provide places for life to get from A to B, but also because they bring different types of water masses in contact with each other. And it's a bit like a city. You've got all the things that are in one current and all the things that are in the other current. So nutrients, for example, different temperatures of water, and they all mix at this boundary between the different currents, and everything can grow there. And so that's all made possible by water moving around the ocean and the speed at which the water moves. The way the ocean moves is it's mostly horizontal. You know, the ocean's kind of in layers, and those layers are moving over each other, and that's the dominant movement. There is a little bit of up and down movement, and it's got swirls in it and currents, and it's doing things all the time. And the patterns in it are set by energy flows, basically, where the energy is flowing from and to. And climate change is having several impacts on that engine. You increase the amount of energy in your engine, what's going to happen?
Hurricanes originate from a process where warm air blows over relatively warm seawater, picks up heat, picks up moisture into that air, and then a early circulation gets started, and eventually that circulation grows into a tropical storm, or maybe eventually reaching hurricane strength. Every hurricane is different from every tornado, and there's a range of wind speeds. So in one particular storm, a Doppler on wheels mobile radar measured speeds approaching 500 kilometers per hour in these tornadoes. And so you can tell that they're quite intense and some of the strongest wind speeds that we've observed on Earth. The maximum wind speeds that came out of Katrina at landfall were about 280 kilometers per hour in comparison. So while, we have extreme weather now, the locations, the intensities, and the frequencies of those will change in the future.
The science behind the greenhouse effect was discovered right here at the RI by John Tyndall using these exact instruments in 1859. 150 years ago, we knew about climate change, and yet still today, we aren't doing enough to tackle the climate emergency we now face. In 2022, in the case of things like climate and COVID, speed is our enemy.
So one of the things that we are seeing an acceleration of is the obvious impacts of climate change. So these extreme weather events, heat waves and so on.
Well, as the climate changes, the temperature, the moisture distributions, the wind patterns will be changing all around the globe. And so there will be certain types of weather events, extreme weather events, that will become more common, more frequent. Certainly things like heat waves. When floods happen, we know that they will tend to be more intense. Consider tropical cyclones in the North Atlantic Basin. The research to date seems to suggest that these will become much more intense, produce heavier rain, stronger winds, and when they do occur, they will be substantially more disastrous when they reach landfall.
Like I'm in the UK, so here we have lots of variability in the weather anyway, so it's hard to spot the extremes, and we are seeing an acceleration of those visible extremes that people are experiencing, which is really drawing attention to climate change. Now, those things have already been very visible in many other parts of the world, particularly places that are vulnerable. So, you know, those impacts are already there and have already been accelerating because of our increased use of fossil fuels and emissions. But I think that where we've not been able to visibly see those effects before, that is accelerating in places like the UK and in Europe.
In a warmer world, you have stronger layers, and that affects the currents. There's a recent study done just in the past couple of years where it has been observed that, I think from 1990 to 2013, the speed of ocean currents on average has increased by 15%. And so people saw that and went, that's a bit weird. And they assumed it was because of wind pushing on the water, because most ocean currents ultimately are driven by wind. But actually, some recent work has suggested that actually, as the layers in the ocean have strengthened, so you've got a thinner layer of warmer water at the top, and it's going to stay there because it's much more buoyant, it doesn't mix as easily. Effectively, when the wind puts energy into the surface current, it stays in a much shallower layer. So instead of making this much move, it makes that much move, and so that bit moves even faster. And so that's the best current explanation for the speeding up of currents due to climate change. And then you get to the effects of all of that on life. And, you know, animals may not be adapted to warmer waters, so they'll tend to move towards the poles where it's a little bit cooler. Maybe their food source doesn't keep up, so so you sort of you reorganize your ecosystems. The mixture of life that you may get may be different, and a lot of species may struggle.
So in terms of how we're acting on climate change, we're acting way too slowly. If we'd acted in the 1990s when many of the discussions were happening, there was opportunity then to take some steps to make some real difference, and that didn't happen because it's a problem of cumulative emissions. So these emissions accumulate over time. So the longer you leave it, the harder it is. That's a kind of basic summary. And because we haven't put in place policies, measures, changes to the way in which we use energy, the types of energy that we use in particular, also having these discussions about how we have agriculture that has lower emissions and so on. Because we haven't had those policies in place in the 1990s, it's now much, much more difficult to do what we need to do, and raises much more challenging questions, much more difficult decisions actually now for policymakers to make than it would have been if they'd made those decisions in the 1990s. So way too slow, and this is why this narrative around urgency and a climate emergency has emerged. It's not just because people are just panicking, it's because actually if you look at the science and the way these cumulative emissions continue to accumulate and how quickly you would have to stop emissions growing and reduce them, it's a whole new set of challenges now than it would have been if we'd acted in the 1990s. What can we do this decade with the infrastructure, with the technologies that we already have? Researchers will and should continue to research what the novel new technologies will be for the future, but we have pretty much all the answers to what we need to do this decade, so we just need to work hard. We need to do a huge amount more to tackle climate change, much quicker, much more, treating it as it is an emergency, not in the way we're treating it. You know, we treated COVID as an emergency. We're not treating climate change like it's an emergency. So we need to actually deal with it in that way, but we can mitigate a lot of the potential damage if we act now. if we don't, it's just going to be much worse. So, you know, the onus is on us to do something right away.
But alongside things like industry, travel, and heating our homes, so too does our desire to go faster come with potential environmental consequences. And as climate change accelerates, burning fossil fuels for the sake of entertainment certainly becomes an issue on a number of levels. We can get places quicker than ever, but progress in how we do so is slower than it needs to be. But we eventually stopped putting lead in petrol, so maybe there's hope yet. This here is one of Alessandro Volta's voltaic piles, one of the first ever electric batteries which he invented in 1799 in Italy. Today, many of those who trade in speed are utilising technology that began right here as they look for more sustainable options to keep going faster.
Motorcyclists tend to be very conservative, you know, it has to go bang. The fact that Ducati are building a performance motorcycle which looks like a performance motorcycle, powered by ions or electrons instead of hydrocarbons, is a really important development. The Ducati engineers said very clearly, this for us is a development platform to develop for our road bikes.
The fastest electric motorcycle is the Vauxhall Wattman, which reached a speed of 455.737 kilometres an hour.
Extreme E is an off-road all-electric SUV championship. We basically race in the most remote locations on the planet that have been selected by scientists as areas that have really suffered from climate change. And then the sponsorship behind the championship goes into building legacy programs to regenerate the areas, so plant trees, clear the beaches, all of these sorts of things, and they're lasting legacy programs. So it's racing without a trace, but also leaving something positive behind. It's an incredible torque that you get with electric racing. You know, as soon as you're on the throttle, it just goes and you get the full power. And it's, of course, you know, there's limitations on battery life and battery temperature, that sort of thing, but actually, in general, it's really fun to drive. It looks like a beast behind me, but actually, when you're in the car, it feels like a race car. It handles well. I think there'll be lots of forms going forward. You know, as technology develops, as all the engineers do what they do, I think there'll be lots of different avenues that are a bit more sustainable than traditional combustion racing, whether that's renewable fuels or hydrogen, electricity, whatever it is. I think that we're going to see a lot of different options open up in the future, which I think is important. You know, I as much as anyone, miss the sound, so if we can find a way to get that back, I think that everyone would be satisfied. But yeah, I think it's a really exciting time to be involved in something so new from the beginning and see the development of that, and see also the effect that that has then on manufacturers and producing road-going cars.
The lighter we can make our cars, the more efficient they go. And this is something that we're definitely going to see and utilise more in the push for electrification. We need to make sure that we are accommodating for the weight that we're adding with these electrical systems. A classic example of that, actually, the Artura behind me is a hybrid car. And we've not only changed materials that we're using to be more lightweight, but we're doing some clever stuff with material science in terms of reducing the number of panels that we put on that car.
E1 is a brand new race boat championship promoting clean electric technologies. And it also utilises hydrofoil technology, which means it lifts off the water, reducing drag and increasing energy efficiency. It can reach higher speeds faster, so with the benefit of instant torque with the electric motor and the fact it rises off the water quickly, it can get to higher speeds quicker. We're currently looking at around 50 knots.
So electric scooters is what the ESC is all about. It's not something that you can currently purchase. It's been totally created from the ground up specifically for this brand new sport. 100 kilometers an hour is the top speed that we've set this to for our riders.
100k standing. Standing, not sitting down, but standing. It feels insanely fast, especially you get a bit of a wobble at the end. And then you got to brake into the first turn. It's really intense, but I love it. I mean, to me, that, oh my God, I'm going to die feeling is pretty thrilling. So I'm a competitive figure skater. We have Olympic speed skaters, Olympic snowboarders, Olympic hockey players. I think the balance is the most important thing that I can take from figure skating into ESC. People don't realize it, but figure skating is actually a really big adrenaline sport. Like to throw yourself into the air, spin 3 times and land backwards on one foot on ice on a single blade is pretty scary, actually.
Really, we're trying to look at past, present, future of motorsport. And then I think Professional Speed helps frame that, because you can look at all the developments over the years from, you know, past, present, fantastic engineers, drivers, cars. And then really, you know, it gives you a sort of backdrop to where we can go as a society going forward, and all the manufacturers, you know, working very hard on that, as you see in the electric avenue. So at the moment, I still think a lot of people are kind of a bit
unsure about electric vehicles and what it means to them. You know, do they run out of charge at the end of the road? You get a lot of these sort of untruths around there. So I think it's all about education, and with the government towards 2030.
As long as governments are there to point the automotive industry in a particular way, look, we are moving to a carbon neutral future, that gives engineers challenges. And the one thing that engineers love is challenges, to try and invent new things.
So engineers and scientists are the ones that are going to solve the current planet's problems. And, sustainability, green, net zero is right up there. And therefore, it makes sense to attempt a new record, but to lead the way as well in the engineering and design to run this car net zero, to demonstrate that you can achieve things and break records, still break records, despite what some people perceive as constraints is, going green and not using fossil fuels. So we're now going to lead the way and show the world that we can actually do this net zero.
As we've discussed, while us humans strive to go faster and faster, there comes a point where some combination of our own biology, the laws of physics, and there just not being a salt plane in South Africa long enough stands in our way. But what about out in the deep vacuum of space where there is nothing in the way whatsoever? Could speed in fact be infinite? No, it can't. So to find out about the absolute universal speed limit, let's head to the fastest place on the planet, Switzerland.
Welcome to CERN, the fastest place on Earth for artificially accelerated hadrons. So these artificially accelerated hadrons are going at 99.9999991% of the speed of light.
The first person to measure the speed of light was the astronomer Ole Römer. And he was following on from work of other astronomers. This is in the second half of the 17th century, from astronomers like Cassini. He was looking at the orbit of one of Jupiter's moons, Io, and measuring how long it took to orbit around Jupiter. But of course, then it takes some hours for the light from Io to reach Earth. But of course, the Earth is also orbiting around the Sun. So there'll be a point where the Earth is closer to Jupiter than it should be if it's in its orbit on that side of the Sun, and there'll be times when it's further away. See, he measured that difference in the arrival time of light from Io as it reappeared from behind Jupiter, and he worked out pretty accurately what the speed of light was. And until then, thereafter, it was known the speed of light is some finite number, about 300 million meters per second. I prefer roughly 1 billion kilometers per hour.
But it doesn't have to be that number. That number comes out because of what we measure in our universe, but it could have been a different number. And it's actually, when you then start to think about the different speeds, if the speed of light was much slower, our universe would look very different. The way we experienced our universe would look very different. The speed that the protons travel at is a result of physics. They're getting ever so closer to the ultimate speed limit, the speed of light. So when the protons are going around the Large Hadron Collider, which is 27 kilometers long, they go around 11,245 times per second.
Until Einstein came along, of course, there was no reason to think that we couldn't find something that went faster than light. Or certainly we didn't imagine it as being some sort of universal maximum speed limit that nothing can go faster. Einstein, with his special theory of relativity, showed that light was special. Or rather, the speed at which light can travel is special. That maximum speed, people say, oh, you physicists, you're just not imaginative enough. Just because you've not found anything to go faster than light doesn't mean it's not possible. But it's built in to the way our universe is structured. It's built into what physicists tend to call the fabric of space and time. It links time and space together. So it's not just some light goes at some speed and we just haven't found anything to go faster. There is no such thing as something going faster than light in our universe.
No object in the universe can go faster than the speed of light, at least relative to other objects. But that talks about objects within the universe itself. You can think of it almost like if you get in a spaceship and you're going as fast as an object can go in the universe, at the speed of light, and you're trying to get to the most distant galaxies that you can see, you'll never actually reach them, because the space itself between you and those galaxies is expanding faster than 1 light year every year.
The concept of galaxies moving away from us faster than the speed of light is something that should make anyone's head hurt. I think I need to start there. As you look further and further away from us, you reach a limit at which point the expansion of the universe is carrying those galaxies away faster than the speed of light, which means that we'll never be able to see those galaxies because their light can't travel towards us fast enough before it gets carried further away.
When Einstein developed his special theory of relativity in 1905, it was actually 2 very important papers. And for most people, non-physicists, and even maybe some physicists, they regard the important thing about relativity is that equation. E equals mc squared. Energy and mass are interchangeable. If you have mass, you can convert that into energy, and the amount of energy you get is the amount of mass multiplied by the square of the speed of light. So a lot of energy from a little bit of mass. But E equals mc squared is not the interesting bit of relativity theory. That's not the profound thing. The profound stuff was in the first paper, which is the fact that the speed of light links space and time together, not energy and mass. It's much more fundamental when we think about it this way. We have to give up this idea of absolute time and absolute space because we're forced to accept that light travels at the same speed for everyone. And it's only then, once we got speed linking space and time together, that we can derive equations like E equals mc squared. So they're like secondary, but they all come back to this important notion that we all see light traveling at the same speed, regardless of how fast we're moving relative to each other.
So when the protons collide and they're both traveling very close to the speed of light, it's due to special relativity that you can't just add those speeds together. But when we're talking about energy, we can talk about double the energy. So each of the beams has a certain amount of energy, and when they collide together, we talk about the center of mass energy. But in terms of the speed, and that's all because of Einstein's special relativity, you can't just add the speeds and say we have double almost the speed of light.
I remember some years ago there was this famous experimental result where particle physicists had created these elementary particles, neutrinos, fired them from the accelerator at CERN in Geneva across to a laboratory under a mountain in Italy.
And neutrinos are supposed to take just a few milliseconds to make that trip because they travel at the speed of light. But what happens is that when you're making this kind of experiment, the neutrinos are not thrown continuously, but they're thrown in very small bunches. And because you have like very good clocks, and you know exactly where you are at CERN, and you know exactly where you are in Gran Sasso, you know exactly when to expect the neutrinos. Well, we saw that on average, these neutrinos actually came a little bit early, about 60 nanoseconds early.
And they claimed initially that these neutrinos were getting from Switzerland to Italy by traveling faster than the speed of light. Suddenly they'd found particles went faster than the speed of light. I, and almost all other physicists, said, don't be ridiculous. You've done something wrong. Nothing can go faster than light. And of course, to a non-scientist, they'd say, well, don't be so arrogant. You should be open to new ideas just because you don't think that Einstein said. Maybe Einstein was wrong.
As an experimental physicist, when I heard that possibly the speed of light had been broken with the faster than light neutrinos, I mean, I was very intrigued, I was very interested, and I always hope that we're going to break the laws of physics and discover something new as we're doing our research. But I was also very skeptical. I think as an experimentalist, I always have to ask myself, what did I do wrong?
So I didn't believe it. So I'm quite a skeptical person. They had, of course, like a sort of like huge reaction from the community, because like if neutrinos really were going faster than the speed of light, we would have had like huge consequences for the laws of physics that we know.
It turned out to be a badly connected fiber optic cable, which it happens.
We've been pretty confident that Einstein's theory of relativity is correct, that nothing goes faster than light, and we understand why nothing can go faster than light. It's sort of one of those non-negotiable things. You know, a scientist should never be 100% certain, but on some things we are pretty damn confident we're right.
So what would it mean if a neutrino could travel faster than the speed of light? Let's say this point right here, that's the present, and let's just say it's an event in the present. So if this is an event in the present, this event can be influenced by what we say all the events that are in a cone of light before it. So this cone of light is determined by the speed of light. So if we think about time traveling in this direction, okay? So all that can happen in here can influence the event right here in the present. But events right here outside of the cone cannot influence the event right here in the present, because they're outside of the cone, and light wouldn't have not propagated from here to the present for us to actually see it. Similarly, our event right here in the present can influence all of these events in the future inside the light cone of the future, but it cannot influence event outside here. But what would happen if something like neutrinos could travel faster than the speed of light? Then this is not respected anymore, and then you could have an event in the past, right here, being able to influence an event in the future without having to go through the present. So sort of like time travel would be possible. And the paradoxes like the grandfather paradox, in which you go back in time and for some reason you cause the death of one of your ancestors, and then you don't exist anymore.
Transport is, of course, the obvious example where an increase in speed has changed our world, but arguably just as influential are the advances in computing. We've seen remarkable change in the way things are run, from word processors to banking to entertainment, like the video game Matt was playing poorly at the start of the film. Overall, our society is just faster than it used to be. There's Netflix and Xboxes where once there were newsreel and Atari cartridges. And so to begin to explore these ideas, we started out at the Centre for Computing History in Cambridge.
So the speed of computers since the early 80s, the sort of the dawn of the home computer era, is just nearly immeasurable. The speed at which your mobile phone works, let alone a laptop, is up in the gigahertz compared with a computer of the early 80s running at megahertz. So these things are just incredibly fast in comparison with what we had back in the day.
I did not grow up with computers, so I saw computers when they were fast enough. We still had modems where we were waiting for the connection to happen.
Getting data from A to B is another area where things have sped up enormously. It used to be on tape.
And one of the components of an educational visit is that they are taken around on a tour of this main gallery. And Commodore 64 becomes a brilliant example, because we do this. We press play on that tape and we wait for that game to load. But instead of standing there and waiting, we take them for a tour, half an hour to 40 minutes tour of the museum. And sometimes when we come back, depending on the game that we are trying to load, the size of it, this might still be loading that game. Which youngster nowadays would tolerate that? You need to load a game, I want it quick. So transistors came about on the electronic scene in about the 1960s. They replaced what were valves. They were fast enough technology. However, fast forward, say, about 10 years, and you could put these transistors, hundreds of them, onto an integrated circuit. And that sped up things, because the number of electronic components that were being used to process your data was larger. The silicon chip started off with a few thousands of transistors, but moved on to billions. It's basically, if you want to dig a hole, you've got one person doing it. Instead of having one person doing it, if you've got 10 people doing it, it's quicker. Computers were very serious machines, so they were used for research purposes, military applications. Everything was really serious.
Leo was a computer that kind of turned that whole thing on its head. Lions had tea shops around the country, and they wanted to computerize effectively their business. Now, this hadn't been done before. So using a computer to make sure all the orders were done in just in time, that the right number of cakes and tea was at the right place at the right time, payroll, all these different things were done by a computer. That was the first time.
You could do everything really quickly. So I think it changed the commercial landscape.
And of course, this increase in societal speed comes with both negatives and positives.
It is an unfortunate fact of being a human in the modern world that the speed of all global change is increasing as time goes on, pretty much all of it. We turned around the ozone layer, but with the exception of that, the problem is that we are, human society and human use of energy, for example, has been expanding almost exponentially. And you can't carry on like that, but it's been on this very steep upward curve. And so the consequences of that are also speeding up and speeding up and speeding up.
If it is innovation that is driving growth, innovation comes from the fact that many people come together and produce more than the sum of the parts. And so it is a superlinear innovation that is taking place. If growth is driven by superlinear innovation, it means that we're going to grow more than exponentially, because innovation is driving this growth. So if this is what is carrying the system forward, then we will need a new set of innovation. Otherwise, we will come to a collapse of our society. So we have a new set of innovation that needs to come into place in order for this growth to be able to be sustained and to slow it down, so to speak, to be able to have all the resources to cope with all the people that are in there. And as you observe in time, this innovation needs to happen faster and faster and faster. So as we are evolving, if innovation is driving growth, we need a faster and faster set of new innovations coming into place in order to sustain that growth. So this is very worrying. I think we are rethinking in the way we're growing. So on the one hand, this idea of livability in the first place, it's becoming something that is more related to sustainability. We're thinking more with respect to the future and so forth. So I think policy is changing in that respect in order to try to look into sustainable cities, but it is a challenge because it is the effort of everyone. We don't need to wait for a government to tell us exactly what to do. We already know the different steps that we need to start doing. Otherwise, yes, it's completely unsustainable.
Technological change is much faster than evolution. And the thing is that we still experience life as humans, right? Our emotions are all packaged in the same chemistry. They don't care about what the computers are doing. And so I think the problem is it's easy to get so excited by the technological change that you forget about being human.
Children need to learn to think like a computer, so computational thinking, rather than actually have the device at their disposal, because that takes away a lot of the logic development and the thinking side of things. The whole idea of, yes, I have this technology, this is new, I'm going to experiment with it. But then few years down the line, you are thinking, oh, what effect has that had on society as general?
But I think you shouldn't forget that the best thing about being human is being human, and it's kind of messy and slow, and it's not something that you can optimize. And if you did optimize it, it wouldn't be any fun. So I think, we just need to be a little bit careful with that.
This whole thing of instant, I want it now. It has to happen now. And that's I feel, the negative effect of speed.
There is one arena of human life where an increase in speed is less of a desire but a necessity that can mean the difference between life and death: healthcare.
I would count something fast spreading as something that can replicate really quickly, something that's really transmissible, and something that's going into a really susceptible population. So it's kind of infectivity, transmissibility, susceptibility. COVID is an example of a zoonotic infection, almost certainly. So it was a brand new infection to us. So you had a very susceptible population. We had no inherent immunity to the infection. And it's also got a very high replication rate as well. So you've got no inherent immunity. It replicates very fast. It's extremely transmissible. And one of the things that we saw, because it's airborne, so this is really important, airborne infections are often amongst the most transmittable. So with coronavirus, what was happening is you had a very vulnerable population and you had an airborne infection. And I think there's a whole cocktail of things that happened. One was the initial communication was a little bit slow to respond. And we've got a world which is much more dominated by international travel. And so that infection from the initial sort of seeds in Wuhan was able to get to quite a lot of countries. And then governments were really quite slow to respond. I mean, if you take the UK, we could see what was happening in Italy. Things were going really, really badly wrong in Italy, yet we weren't sort of taking action quick enough. So there was a mixture of vulnerability, sort of slowness to respond with a brand new virus that our immune system has never seen before. And it was a virus that was able to really quite quickly overwhelm the immune system, unfortunately, in quite a few people. Ironically, it was our slowness that let COVID spread so quickly.
Here in the UK, as wait times for ambulances and routine appointments have skyrocketed thanks to the absolute incomprehensible in the Western world, it's possible that drones could play a vital role in improving speed within healthcare.
There's so many drone manufacturers in the market, but nobody's actually utilizing the technology. So the technology is there, but nobody's using it for good. So we focus on three things. You save money, time, and lives. The medical delivery really goes into two aspects, and it's first of them is the time-sensitive emergency ad hoc use case, which is organ transplant, emergency equipment between hospitals. And the second use case is the more routine deliveries between, let's say, your GP back to the lab and then back to your GP again.
But while drones can certainly be part of our healthcare future in places like London, they are far from a complete solution. Founded in 1986 by Andrea and Barry Coleman, along with American motorcycle legend Randy Mamela, Riders for Health is an African-led social enterprise. Along with its partner charity Two Wheels for Life, they have changed the way healthcare is delivered to over 47 million people in places like the Gambia and Lesotho, providing speedier, more reliable healthcare to rural African communities.
Transport's a big issue in Africa because very few people are trained to run and manage vehicles, and also the terrain's so difficult, the distances are huge. There are very small communities very far from centres, and so often health workers have to walk. So for us, the motorcycle is really the perfect tool for the job. It gets the person there, it does the job quickly. It doesn't mean that drones aren't going to be useful, because they will for certain things, but nothing is the only answer.
We are saving lives. These delays are happening, they cause death to women and children. Our interventions are helping a lot. We now have ambulances, well maintained, to take any woman in labor on the spot to the next higher level of care.
So maintenance and speed are tied together.
Who can pay for life? Can we pay for life? We cannot. But we do what we can to save lives.
So speed for us in that context is vital.
Imagine women walking 5 kilometers. That's about 1 hour of walk with a baby behind her back to come to the clinic that's on outreach to meet nurses. Imagine walking that long and no nurses, no staff. How would the poor woman feel having to walk back the same distance with a sick baby, probably, no vaccination for her baby or herself, no care for her baby or herself,
And in diagnosis, when you're talking about a disease like Ebola or COVID, you have to detect that disease in communities, get the results through quickly. Before we were doing sample transport for diagnosis in Lesotho, it was taking maybe 3 months to get a sample, a blood sample, from a patient to a health centre, get that to the clinic, and get the report back. We can now do it within 7 hours. And so that kind of speed is vital in terms of the healthcare of the population of Africa.
What are you doing? There's no time for big, dramatic, sweeping shots. We're not going to overrun. We haven't even talked about the speed of sound yet. Hurry up. Cut to the sound studio. Go.
The speed of sound is unbelievably slow compared to the speed of light. I mean, we're talking 343 meters per second as opposed to millions. It means that even the distance that I am to you, we're talking in a number of milliseconds of delay. But of course, then usually by the time you're looking at big screens in, for example, an arena or a stadium setting, for the people right at the front, it's going to be out, the sound is going to be ahead, and for the people right at the back, the sound is going to be behind. And there is just no way to fix that. If you have a bell and you have someone hit it once a second, as you walk away from it, you'll notice that it gets further and further and further out between what you're seeing and what you're hearing, because the light is hitting you pretty much instantaneously, and you know, for every meter that you move away, the sound is delayed by about 3.5 milliseconds. What's really interesting then is that when you get out to be about 343 meters away, you're back in time as you see it with your eyes, but then you get the person to stop hitting the bell and you hear one bell strike after they've stopped, after you see them stop hitting it, because you've actually come all the way through the cycle and you're a whole bell strike behind. So when you start messing with the relationship between what we're seeing and what we're hearing, your brain kind of goes into fight or flight mode. In the order of 10 milliseconds is where most lay people will start to perceive that there is an issue. So that's the thing basically with system design. You've got to get all of those timing parameters right. And I'm sorry if that was distracting, but that's exactly what I'm talking about.
We've almost reached the end of our time, and yet there's still so much we haven't even talked about. Hummingbirds and comets, lava flows and telecommunications, shutter speeds and frame rates. We haven't called this film an incomplete history because we're lazy. It's just too big of a topic. If you want to learn more, there's hours and hours of extra content available by subscribing via the link below. And of course, to ever truly understand speed, you need to experience it. Perhaps watch this film again, but while on a roller coaster. But before we go, now that he's had a whole film's worth of time to practice, let's check back in and see if Matt has got a better handle on speed via the PlayStation.
Okay, so I feel like I'm gradually getting to grips with speed, acceleration, grip, and it's been kind of fun to have like a hands-on education in, come on, please turn. Ah, stayed on the bike, didn't stay on the track, but you know, one step at a time. If nothing else, I'm glad that we don't have the budget to put me on one of these bikes for real. Turns out we got the budget. I'd like to say thanks to all the Patreon supporters of Cosmic Shambles. Thanks a lot for providing the extra funding required, which meant they could send me here to the British round of the MotoGP. You can hear bikes going around the Silverstone racetrack, which we are like in the middle of right now, and so I can experience the giddy thrill of acceleration and all the other derivatives. They're going to put me on one of these GP bikes, send me around for a lap. So I know what I'm in for. I'm here with Simon Crafer, previous GP rider. You won the British Grand Prix?
Yeah, a long time ago now. Yeah, 98.
Okay. So my main question is, because they're going to put me on this 2-seater later today, what am I going to experience riding on one of these bikes?
I think it's going to be a little bit scary, obviously. Okay. One of the big ones that'll scare you is the braking, you know, because it's one of the biggest G forces. And then once you get it picked up again, it's going to rocket forward. You know that when you do something dangerous and you giggle because I got away with it?
I get like that in some calculations. Yeah.
You're going to get it today.
Yeah.
For an experience as terrifying and life-changing as this, you want to have friends around to support you. Failing that, I've got Hannah Fry. You just happen to be strolling around.
Just having a nice day.
There you are.
MotoGP, here you are.
Yeah, so you might think Hannah's here for emotional support.
No. Quite the opposite.
Checking the maths.
I am.
It's going to be.
I passed. I have a heart rate. It's not too high. My blood pressure is adequate.
This bike is 250 horsepower.
with just 150 kilos. Roughly 300 kilometers an hour.
My body can decide.
Yep, size.
Look where we go.
Oh, God, yep. Yeah. There is less seat than I expected. Okay, that is the single most terrifying experience of my life, past and future. Oh my God, I can literally see through time. Everything I thought I knew about friction is a lie. There's no way that bike could, like, we were going around corners, lying down. Oh my goodness. I've never been so acutely aware of my own inertia. That's... Okay, they say you only do one lap, and I was like, just one lap, but first two corners, that was enough. Could have got off then. That would have been the whole experience, but oh my goodness. Oh, my heart is racing. Oh my God, oh my God. Oh my God, Al. That's the most outrageous experience imaginable. Like, honestly, you have no idea how much momentum your body has. The things I did in there. Yeah, look at that, right here.
Oh, Lord.
I can't.
Look, Newton never went
We
on
have
a
been, no, exactly. If Newton had gone on a motorbike, physics would look very different. It's now one day later, Matt, and I think the adrenaline has finally worn off. So after the race, my heart rate stayed at above 100 BPM, and my resting is like 50s, like I was 60 before the race, and it took a good 15, 20 minutes before I came back down below 100. My hands were shaking for about an hour afterwards. I couldn't hold them still. I think that's just not a biologist or a medic. I assume that's just the adrenaline, but it shows you that, don't get me wrong, when I do the calculations, I get a giddy thrill. But as much as you understand the mathematics, you understand the science, you've actually done the working out yourself, until you experience speed, acceleration, its other, derivatives, you haven't got that kind of intuitive, visceral sense of what's going on. You've got to actually go out there and try it for yourself to fully understand the terrifying not conveyed by the science.
Speaking from experience, I can tell you there is no doubt that the two-seater ride gives you a true understanding of what it means to be rapidly moving through space. And whilst neither Matt or I had any control over that speed, where we do have control, should we continue to accelerate or do we need to slow down? A motorcycle racer uses their understanding of risk versus reward in their pursuit for more speed. Maybe we need to be doing more of the same. In the case of climate change, civilization is already beginning to experience the problems of hurtling forward at speed without properly mitigating the risks, or worse still, ignoring the warning signs. The planet is furiously waving the yellow flags. But since a time when we were just using speed to run away from cave bears, we keep desiring to go fast, to run faster, to drive faster, to fly faster, to expand and progress faster. And no doubt we will continue to push boundaries where they exist, because that's what we do, but hopefully in ways that benefit us all. We are now in a position where we can push those boundaries in a better way. We can still go racing, but we're starting to do so in a more sustainable and safer way. We can continue to grow our cities, but with better planning, better economic policies, and with renewable energy. We can aim to slow down the speed of invasive species and habitat destruction. and we can still get places quickly, but let's do it in a safer and smarter way. And best of all, sometimes we don't have to go anywhere quickly at all. And then at other times we can, just because it's damn good fun.
The fastest bathtub was fitted with a 4-cylinder Yamaha R6 engine and reached a top speed of 189.9 kilometers an hour.
Chuck Yeager, the first person to break the sound barrier in a plane, often said that speed was relative, that he realized the real barrier wasn't in the sky, but in our knowledge and experience. If the faster we go, the more we learn, let's not waste those lessons. We can't change the speed of light. We can't alter how fast this ball of rock and water is surging through space or how fast space is expanding. But what we can do is use the same curiosity and desire that makes us want to race each other around a track, examine the nature of the universe, and deliver a faster medical diagnosis to ensure we can continue doing all those things long into the future, as long as we continue to feel the need. No. We've gone the whole film without saying, I'm not doing it. I'm just not. I'm not doing it.